Let's finish with the last two properties. We will review ionic charge and talk about ionic radii or ionic size, and we will also look at metal and nonmetal reactivity. Recall that an ion is an atom with a charge. That means that it does not have equal numbers of protons and electrons. A cation is positively charged because it will have more protons than electrons. That is because a metal loses electrons. An anion is negatively charged. It will have more electrons than protons, and that's because nonmetals generally gain electrons. One of the first things that you need to know is that cations are smaller than a neutral atom. You can tell that by looking at the size of the lithium ion compared to the lithium atom in this diagram. Now, why is that? Recall that the energy levels of the lithium atom would be 1 and 2, and there is 1 valence electron in that outer second energy level. If you are a cation, you want to lose electrons, and the lithium ion, because it has a +1 charge, loses 1 electron. When that electron disappears, you now have only 1 energy level. That energy level is closer to the nucleus, and we know that the nucleus is strong and is positively charged, and it will pull in that inner shell, creating a smaller ion. You can also think of it as a tug of war. We know that there are 3 protons in the lithium atom and 3 electrons. When the lithium ion is formed, it still has 3 protons, but now it has 2 electrons. Because there is a greater number of protons in the nucleus than electrons, the electrons get pulled closer to the nucleus because of that high nuclear strength. Anions are larger than a neutral atom. If we take a look at this example, you can see that the oxide ion is greater than the oxygen atom. Well, why is that? Once again, we're going to go to the oxygen atom, and we're going to realize that there are 2 energy levels, and there are 1, 2, 3, 4, 5, 6 valence electrons in that second energy level. We know that anions want to gain electrons, and so there will be a gain of 2 electrons to the oxygen atom to form its ion. Notice that those 2 additional electrons were placed back in the second energy level. So we haven't changed energy levels, but what we did change was the power of the electron. Because there are more electrons in the second energy level, there are more electron-electron repulsions. And because of that, they're going to push away from each other a little bit, and they're going to make the ion a little bit larger than it would be in neutral form. We could also think of the tug of war again. Remember that the oxygen atom has 8 protons and exactly 8 electrons. But the oxide ion has 8 protons and now 10 electrons. So the electrons are winning out of the tug of war, and they are going to pull away from the nucleus, thus creating a larger ion. This diagram shows you a little bit about just regular atomic size and ion size as well. Recall that atoms will increase in radius as we go down, and as we go across, we find that atomic radius is going to decrease. We find that the same trend is going to happen for ionic size as well. If we take a look at the lithium, sodium, and potassium ion, once again you can see that the ionic size is going to increase as we go down, whether you are a cation or you are an anion. If we take a look at the cations as we go across, you can see we're going from 95 to 50, and that's a decrease, just like if we were looking at the sodium atom versus the aluminum atom. Remember that there is a staircase line that separates the metals from the nonmetals. So if we're looking at anion size, you will notice that, and you really can't tell in this picture, but ionic size for anions will go in the decreasing direction as well as we go from left to right, but it kind of starts all over at the beginning of that break. You'll notice that the chloride ion is 181 and the aluminum ion was only 50. So we say that the cation size decreases and then the anion size decreases as well, but they have the starting points at the far left of their at their borders. This is just another diagram showing you once again the group trend of increasing as we go down for a cation and an anion, and as we go across, the period trend is decreasing. This is a better picture to show that process of the ion decreasing in size for the cation, and then there's that break because of the start of the nonmetals, and you can see it starts big again and starts to get small. Let's take a look at two examples. The first one says we're going to arrange in order of decreasing ionic radius, and they give us the phosphide ion, they give us the magnesium ion, and they give us the chloride ion. So let's go ahead and circle those. Got the phosphorus, the magnesium, and the chloride. Now they are all in a row, which is a period trend, but hopefully you'll notice that there was a cation given to you. And we talked about how cations are always smaller than the neutral atom. Anions are generally larger than the neutral atom. So if we're going from largest to smallest, the magnesium ion is going to be the smallest. And that means that we're now comparing the phosphorus and the chloride ion, which is these two, and we know the general trend is as we go to the right, it's going to get smaller, which means that phosphorus is going to be the largest one, and then chloride will be in the middle. We take a look at the second example, all of the ions are going to be in a group, and they are all cations. We know that pattern is as you go down it gets larger. We want to put this in order of increasing size, and so lithium is going to be the smallest, then will come potassium, and lastly the cesium ion. The last property we're going to talk about is reactivity, how chemically active or reactive an atom is to another atom. We're going to first look at the metals, so I'm going to draw in the staircase line that separates our metals from our nonmetals. And then we'll state the trend, which is as you go across, metal reactivity is going to decrease, and as you go down, it's going to increase. I want you to recall the video that we watched when we looked at the properties of alkali metals with water. As lithium, sodium, potassium, and rubidium got dropped in water, we successively saw more explosiveness. That is an excellent way to remember that the reactivity of metals increases as you go down a group. If we go across, if you think about properties again, we talked about how the alkali metals are the most reactive. We said that group 2A were reactive but not as reactive as group 1A. And then we talked about how the transition metals were somewhat unreactive. So that should also help you remember that as you go across, metal reactivity is decreasing. This pattern basically comes down to ionization energy, the energy required to remove an electron from an atom. We find that the most reactive metals will have the lowest ionization energy. It will not take a lot of energy to get an electron removed from its atom, and that's what makes it very active or very reactive. Recall that at the lower left end of the periodic table, we have the largest atoms. Those atoms are going to have an easier time removing an electron because they have a weaker nucleus, and that the elements towards the left side of the periodic table have a smaller nuclear charge than the metals on the right side of the periodic table. Thus, their nucleus cannot hold on to their electrons as tightly. Let's draw that staircase line in again, but this time let's look towards the right side. We'll find that the non-metal reactivity trend is opposite of the metal reactivity trend. As you go across, it's going to increase, and as you go down, it's going to decrease. And there's a really easy way to remember that. Remember that fluorine is the most electronegative atom. It has the greatest tendency to attract electrons to oneself because it has a super strong nucleus. This makes for a very small atom, so the nucleus can hold on to its electrons really tightly, and it can also take electrons from other atoms with ease. The reason for this pattern is ionization energy as well, but also electronegativity. Because the most reactive nonmetals are going to have the highest ionization energies, that means that most atoms will not be able to gain enough energy in order to have electrons removed from the atom. However, with the greater electronegativity value, they have a larger tendency to attract electrons to oneself, and basically that comes down to the fact that in the right side of the table we have the smaller atoms with the stronger nuclei, and stronger nuclei mean that they can take electrons from other atoms as well as holding on to their own. So high ionization energy and electronegativity values are the reason why we see the non-metal reactivity trend. This concludes our 5 properties, and hopefully you will review in class, and if you have any questions, I'll be able to answer them next time I see you.